Let's now take a look at transverse wave and longitudinal wave. Before that, we need to note that both these waves are termed as progressive wave, which is created by a movement of disturbance from a source when energy and momentum of the source move outward in the direction of the propagation. Transverse wave is a progressive wave in which elements in the medium oscillate in the plane perpendicular to the direction of energy travel. Longitudinal wave is a progressive wave in which elements in the medium oscillate in the plane that is in the same direction as direction of energy transfer. It is important to note that words that shouldn't be used in describing transverse and longitudinal wave is words like vibrate, oscillate is the more accurate term, as each of the particles is undergoing simple harmonic motion. Second, we no longer use the phrase that in the direction of the propagation of the wave, since the focus should be on the direction of the energy transfer. Let's recap some fundamentals that you learned at O level on transverse wave. In transverse wave, you can see that if the direction of the wave movement is in this direction, then after time delta t, what is dotted is the position of the wave, and it may appear that the wave has moved, but actually what happens is that the particles are actually oscillating up and down, and hence we can conclude to say that the particle at this position oscillate downwards, while the particle at this position oscillate upwards. Next part to recap is that in this graph that we're studying the displacement, the vertical displacement versus the horizontal displacement. And therefore, the wavelength is still governed by this. This will be the wavelength, or is also the distance between the trough, or the distance between the adjacent crest, or consecutive crest. There's also another graph that we can use to study transverse wave, which is by looking at vertical displacement versus the time graph. So in this case, we're looking at one particle, and the particle is undertaking simple harmonic motion. So we can assume it is moving in this direction, and from there we can plot the various positions of the vertical displacement. And from this graph, we can be able to identify the period, which is again between two adjacent or consecutive crests, or if not, between two consecutive or adjacent trough. We're also able to identify the amplitude of the transverse wave from this graph. Let's now take a look at the longitudinal waves. Specifically, a good example is that of sound waves. So in the case of sound waves, initially when undisturbed, they are in these positions. Subsequently, they could be moving towards a point or away from a point. Subsequently, the direction of travel could be in this direction, from left to right or right to left. Let's take a look at compression and rarefaction. For both compression and rarefaction, both the particles have zero displacement. They do not oscillate. But in the case of compression, as you can see, all the particles on its left has positive displacement. So they are moving from left to right. While all the particles on its right has negative displacement. So they are moving from right to left. Hence, because of this, we can conclude to say that there is a clustering of particles at this spot, and hence the term compression, and the reason why at compression it has the maximum pressure. Let us now take a look at rarefaction. In the case of rarefaction, the particles on its left has negative displacement. So all the particles are moving from right to left. The particles on its right have positive displacement. So they are moving from left towards right. So based on this, we know all the particles are actually spreading as far away from the point of rarefaction, which is the reason why rarefaction has the minimum pressure and the air particles around the region has the lower density. And similarly, in the same vein, we are also able to predict the wavelength by looking at the positions, by measuring the distance between adjacent maximum pressure or adjacent compression, or otherwise we could do so by also determining the wavelength from the positions of the minimum pressure or from the distance between consecutive rarefactions.